Hello and welcome to our first tutorial that is intended to help you with the assignments. So the assignment 1, the deadline is already complete and many of you have successfully submitted the assignment. This tutorial is for assignment 2, and again, for if you've already worked on assignment 2 and you're fairly confident, you don't need this tutorial. It's really meant for those who are finding the assignments a little difficult, and we're not going to be giving the answers during this assignment, but we are going to help you with each question to the extent possible to kind of have you start thinking in the correct direction. Okay. So what I have in front of me is a screen with it's a printout essentially of the assignment paper, and I'm going to be going step by step in talking through the questions. So let's jump right in. So the first questions 1 through 4 all pertain to the same description. Okay, and I'll highlight it here. So that's questions 1 through 3. And then question 4. Okay, so questions 1 through 4, that's what we're going to talk about during this during the first thing, and they all pertain to a single graph. So this one graph kind of covers the description for all the 4 questions. And the important thing to note here is that it's a continuous random variable, and it represents a cumulative density function. That's very important. So it's a CDF and not the PDF of the distribution. Okay, but even before we jump into CDFs and PDFs, the important thing is it's a continuous distribution, right? So it's a continuous random variable. So with continuous random variables, you already know that the probability of a particular event is 0. And you could, if you're asking questions like the probability between that the event if you present a range, right? So if you present a range saying what is the probability that a failure will occur between 1 and 3 hours or between 2 and 4 hours, if you give it a range, then with the PDF you're really interested in the area under the curve defined by between the 1 and 3 hours. And so you can rephrase that question as in less than 1 hour, in which case you're really talking about the lower limit, in which case is 0 hours, all the way up to 3 hours. Or you can frame the question as what is the probability that it will fail after 2 or 3 hours, in which case you're interested in the area under the curve that starts at 2 hours and then goes up all the way till the upper limit. In this case it's 4 hours. Now all of this is true for a PDF. Now the core principle still holds in that the probability of a point event is 0. So the probability of if you're not talking about a range, and a range can be defined as the probability that it will fail in less than 2 hours, the probability it will fail in more than 2 hours, probability it will fail between 1 and 3 hours. For all of those you can get an exact answer, right? A non-zero answer. But if you ask the question what is the probability it will fail at exactly a particular point, the answer is 0. Now with the PDF you're always interested in the area under the curve associated with the range, but by definition the CDF is nothing but the area under the curve to the left hand side of the PDF for a given point. So if someone is asking you the question, the probability that something will fail before a particular point of time, in the PDF you might have been interested in the probability from the lower limit, which could be 0, and all the way to the point under question. So if someone says what is the probability that the air conditioner will fail before 3 hours or something, in the PDF you would be interested in the area under the curve from 0 all the way to 3 hours. But because the CDF is by definition the area under the curve of the PDF up to that point, you don't have to look at the area under the curve, you just have to look at that point. You just have to look at the y value at that point. So if the question is the probability it will fail before X, look at the value of Y at X on the CDF. If the question is the probability that it will fail after, and the fail after can be asked in many ways, that it will not fail before or in other ways, then you just care about 1 minus the value of the CDF at that particular point. So that should, in a sense, at least help you answer questions 1, 2, 3, and 4. Okay, so simple rule: if given PDFs, you care about area under the curve to answer probability questions associated with ranges. If given CDFs, you just care about the Y value at a given point. If the question pertains to the probability of an event occurring before, if it's a probability of the event occurring after, you care about 1 minus the probability of what you will see on the y-axis at a given point. Why? Because by definition, a CDF is the area under the curve of the PDF from the starting point, which is 0 in this case, but it could be minus infinity in others, all the way up to the point under question. The area under the curve on the PDF from minus infinity or 0 all the way, whatever the lower limit is, up to the point under the question, that area is what is being plotted in the CDF. So if the question has to do with what is the probability something will happen before, then just take the Y value at that point. If the question is about what is the probability that something will not happen before or it is going to happen after, then you care about essentially the area under the curve on the right hand side of the PDF, which is the equivalent of saying what is 1 minus the Y value that you have on the CDF. Okay, and just also note that how at the value 4 your probability is 100%, right, which means the probability that something will fail before 4 hours is 100%, so it's definitely going to have happened. Okay, so that should help you answer the first question. First 4 questions. With respect to the central limit theorem, it's more of a definition, so we won't really focus on that. Let's go to the 6th question. For the distribution n of 0, 5 square, and we usually mention it as something square, just so that it's very clear that 5 is the standard deviation. So 5 is the standard deviation, so obviously 5 square is the variance. We ask the question, what is the distribution of the sample mean given a sample size of n? And we've discussed this before in that the sample mean stays normally distributed. So you know that. You also know that the distribution of the sample mean, the mean of the distribution of the sample mean is the same as the distribution of the data itself. So there's no new bias being introduced, so the mean should not change. And you also know that the standard deviation gets scaled down by a factor of square root of n. So you could either think of it as this new standard deviation should be, if the old standard deviation was 5, the new standard deviation should be 5 divided by square root of n. Or you can think of it as if the old variance was 25, then the new variance would be 25 divided by n. So it's either the new standard deviation is 5 divided by square root of n, or the new variance is 25 by n. Okay. Moving on to question 7. If the null hypothesis of a statistical test is that mu is less than 10, then the alternate hypothesis would be. What you really want to think of the alternate hypothesis, you want to think of the null hypothesis plus the alternate hypothesis covering the entire universe. So if the null hypothesis could be 10 or less, then the alternate hypothesis really would be the rest of the possible mu's that would not overlap with what the null hypothesis covers, but it's collectively exhaustive. So all the other possible mu values are getting covered. Okay, and okay. So moving on to the next question, question number 8. The HR department in a company believes that employees of a specific designation should be compensated more or less equally. And they are of the belief that the variance in compensation of all associate managers should not be more than 22,000 rupees. However, they do not have the compensation information for all associate managers in this company. So the idea behind saying that is that if they had the entire data, that this would not be a exercise in inferential statistics. They unfortunately have to take a sample in order to do this. So they take a sample, and what they find is, so they commission a survey and receive data on compensation for 16 associate managers. Which hypothesis test would you use to see if the variance in compensation is less than 22,000 rupees? So, I mean, the main thing that you need to focus on here is that this is a test where your data points are ones that tell you the compensation of each manager. But what you're testing it against is the variance. So it's just really important for you to see which test is a test to compare variance and standard deviation. And the other thing is also that because you're comparing it against a benchmark number, it should be a single sample test. Okay? Good. We move on to the next question. Now, question 9 through 11 pertains to the following description. A teacher typically grades her class 30% A's, 40% B's, 20% C's, 6% D's, and 4% F's. What is the probability of getting a B or better for a randomly selected student? The important thing to recognize out here is that while you are given a breakdown of each grade, the question that is being asked of you is only about getting B or better, right? So you can essentially, you must see this as B or better is, you know, B and A is B or better, and C, D, and F is worse. So you just have to break that into two binary bins and report the probability there. With respect to question 10, in a class of 10 students, what is the probability that more than 2 students get grades D or worse? Because it's again presented as D or worse, there are only 2 possible outcomes. Either it's D or worse, which means you get a D, the probability of D and F, or it's the other way around, which is better than D, right? So the probability of being A, B, or C. So there are only 2 classes, and it becomes kind of like a Bernoulli distribution. But now you're asking the question is, what is the probability that 2 people out of 10 get worse? So the way you treat this is exactly like a binomial distribution. And the important hint out here is that you're asking a question about the probability that 2 or more students, you're not asking, see, it's a binomial distribution, and so it's a discrete distribution. So you could get an answer for what is the probability that exactly 2 students get, exactly 2 out of 10 students get grades D or worse. But that's not what is asked. What is being asked is what is the probability that more than 2 students out of 10 get this probability. And the answer to this question would become very hard if you use the binomial distribution formula and calculated the probability of 2 out of 10 getting grades worse than D, 3 out of 10 getting grades worse than D, 4 out of 10, and going all the way to 10 out of 10. The easier thing to do would be to see what is the probability that 0 out of 10 students gets grades worse than D, 1 out of 10 students gets grades worse than D, 2 out of 10 students get grades worse than D, and then add those 3 probabilities up, and then just do 1 minus that number. Okay, that way you're able to answer the question of what is the probability that more than 2 students get grades D or worse. You do that by calculating the probability that less than 2 or less students get grades worse than D, and doing 1 minus that probability. So that should kind of help you answer that question. The next question, 11, also pertaining to the same thing, is in a class of 50,000 students, what is the probability that more than 5,050 students get grades D or worse? We just use the normal approximation to the binomial because it's a very large number. You don't want to be calculating 50,000 C 50-50 or whatever. The simple thing to do would just be to do the normal approximation. And if you were to do the normal approximation, what would be the mean and variance of this normal distribution? It's quite simple. N, which is 50,000, times P, which is the probability that a student would get a worse grade, get a grade worse than D. That is P. So n times P is the mean of the binomial distribution. So this would be a normal distribution with that mean. And similarly, you can look up the variance of the binomial distribution, which is nothing but n times P times 1 minus P. So if you use those two formulas, and then now you know the nature of the normal distribution. So it will become a normal distribution with that mean and that variance. What is the probability of getting a value greater than 50-50 on that normal distribution? Simplest thing to do is just find out the mean and variance of the normal distribution and get that p-value by plugging in like a function that was shown to you in Excel. So you can just use that kind of norm dist function that we had in that was shown to you in the class, and you can plug in those values, and that will give you the answer to this question. So use Excel or use a statistics textbook after you figure out the parameters, that is the mean and variance of the normal distribution that you have on your hands. And on that normal distribution, you want to know the probability that more than 5050 students get that value. So you want to know the probability of getting a number greater than 5050 on a normal distribution with a mean equal to 50,000 times the probability of getting a grade D or worse, and a variance of 50,000 times the probability of getting a D or worse times 1 minus the probability of getting a D or worse. So that's NP times 1 minus P for the variance. So the next question, which is you decide to test the hypothesis that the average time for a technician to complete a task is 15 minutes. You don't know the population standard deviation. You've collected 14 data points in this regard. What test would you use? So the important thing to think about is you start by kind of eliminating what are you testing. You're trying to do a test on the population mean, because you're testing a hypothesis at the average time for the technician. So this is not a test on standard deviation or variance, it's a test on mean. And so out of these 4 tests that are given as choices, only 2 tests are used to test the mean, population mean. And with 14 data points, if you know the population variance, you use one test. If you don't know the population variance, you use the other test. So that should help you eliminate between these 2 options and give you one option. Okay, so now taking the same example from question TEL, you calculate the test statistic for the appropriate test and find the value to be 1.3. In order to get the p-value, which one of the following would you calculate? So here's a graph with 1.3, and the question is, do you want the probability of getting a value less than 1.3 in a norm? So what is this? So I've said that this is either a standard, normal, or a t-distribution. So we don't, because it depends on what the test statistic is, right? And the important thing to realize is that once you narrow down on which test it is on question 12, that should logically tell you which distribution you want to be looking at in question 13. Okay? So if you choose to perform a z-test, you would be looking at a normal distribution. If you choose a t-test, you will be looking at a t-distribution. And the couple of other things that you would need help with is always remember that with a z-distribution, you don't have anything to do with degrees of freedom. With a t-distribution, you have to mention the degrees of freedom. And the degrees of freedom is always n minus 1, where n is the number of data points. Okay? The second thing to realize in terms of choosing between the choices here is, is it a one-tailed test or two-tailed test? A one-tailed test typically will be framed like, what is the probability? The null hypothesis would be something where you ask the question such as, is the average time less than or equal to some value? Is the average time greater than or equal to some value? Those are typically one-tailed test. If you're asking the question, is the probability less than or equal to some value, you like to look at the right-hand side of the distribution after you calculate the test statistic for your p-value. If your null hypothesis is one of asking the question, what is the probability of that this average time is greater than or something greater than or equal to a certain value, then you'd like to look at the left hand side of the distribution. If you ask the question, is the average time equal to a certain value, then it becomes a two-tailed test. So you would calculate the test statistic, and the easiest way to make it a two-tailed test is to multiply by 2. So see what question is asked, and that should help you answer whether it's a normal distribution or a t-distribution, how many degrees of freedom are involved, and whether you like to get the probability of a value greater than, probability value less than, or the probability of the value which clearly cannot exceed 1. The probability can never be more than 1. So if you're looking at both sides of the tail, which probabilities would you be interested in? Okay, so hopefully this tutorial kind of helps you answer some of these questions, and we look forward to most of you successfully completing assignment 2 and submitting it without too many errors. Thank you.